So really well done for getting this far. This is the last video of section 2. We're going to think about stationary points of functions of two variables. Okay, so here is an image of the energy surface in a molecular reaction. Okay, and don't worry about the details, but basically there are two variables that you can change, okay, the x and the y, and this gives a different function, okay, that is this surface. And the height is the energy, okay. So to have a certain molecular reaction, you have to supply energy to get over these hills, okay, or go through the mountains. And this is one example of where you need to know about the shape of a function and to be able to determine the maximum and minimum of a function of two variables, okay, of a surface. Okay, so we're going to first think about a function of two variables, f of x and y, okay, and we're going to consider a stationary point. So a stationary point, so if the stationary point is AB, this means that the first derivative of the function with respect to x at this point is equal to 0, and the first derivative of the function with respect to y evaluated at this point AB equals 0. Okay, i.e. the function is not changing at this point AB. Okay, so we considered these maxima and minima before for a function of a single variable. Okay, and we saw the Taylor expansion gave us either a parabola that was a smiley face or a sad face. Okay, or we had this point of inflection. And we have similar cases in the function of two variables, and that's what we're going to look at now. Okay, so if we think about the Taylor expansion of the function of two variables, we have f of a plus h, b plus k equals f of a, b plus h f x, okay, evaluated at point AB, plus k f y, so df by dy, partial derivative, evaluated at point AB, plus 1/2 h squared f x x evaluated at point AB, plus 2hk f x y, okay, this derivative again evaluated at AB, plus k squared f y y. Okay, now at the stationary point, the first derivatives are 0, okay? So these things are 0 at the stationary point. Stationary point, these are 0. Okay, so at the stationary point, we have that the difference in the function, so f of a plus h, b plus k, minus f of a, b. Okay, so this is the change in the function as you go from a point a, b, to a different point, a plus h, b plus k. Okay, this is x and this is y. So the change in the function is equal to this second order derivative term, okay, plus higher order derivatives. Okay, so let me just clean this up. Okay, so at the stationary point, the difference in our function, okay, at the two different points, is this bracket, 1/2, I'm going to use a curly bracket, h squared fxx plus 2hk fxy plus k squared fyy. Okay. Now I'm going to take out a factor of fxx. Okay, because remember, this is a derivative, but it's evaluated at the point a, b, so it's just a number. Okay, so we're going to take it out, and this leaves us with h squared fxx squared. Okay, now note this is a square, it's not a derivative. So this is d2f by dx squared, evaluated at ab, and then that whole thing gets squared. Okay, plus 2hk fxy, and now because we're dividing by fxx, we need to add that here, plus k squared fxx fyy. Okay, and we're going to write this as a square, so 1 over 2 fxx. We're going to write this as h fxx plus k fxy, all squared. Okay, so if we square this, we get h squared fxx squared, that term. We get k squared fxy squared. Okay, which we don't have above, so we need to take away k squared fxy squared. Okay, we get 2hk fxx fxy. Okay, which is this term. Okay, so the square of this gives this term, and a term like this, we have to take that away. Okay, and then we've got plus k squared fxx fyy. Okay, so this is something squared, okay, minus k squared, and let's call this thing, let's call it plus k squared delta. Okay, and here delta is defined by fxx fyy minus fxy squared. Okay, so we find that the difference in our function, f of a plus h, b plus k, so the function evaluated at this point, take away the function evaluated at ab, is equal to 1 over 2 fxx. This thing that's squared, h fxx plus k fxy squared, plus k squared delta. Okay, where this is delta. Okay, so if we think about how our function changes, so this term is squared. Okay, so this is always positive. This is always greater than 0. Okay, so the nature of the change in our function will depend on the sign of delta. Okay, so k squared, that's going to be greater than 0. So we have to focus on this delta. Okay, and we get different cases. We find if, oh yes, and the sign of this. Okay, so if delta is greater than 0, okay, and fxx is greater than 0, then what does that mean? It means that the difference between the function here and here will be positive, a positive number. Okay, so if we start out here, okay, at fab, and we move to a plus h, b plus k, then our function increases. So what does that tell us about this stationary point? Okay, if we're at this point and we move in any direction, the function increases. It means we're at a minimum. Okay, so this means we're at a minimum. Okay, if delta is greater than 0 and f xx is less than 0, then the difference is less than 0. Okay, then this thing becomes less than 0. So it means we start here, and any direction we move, our function decreases. Okay, so this thing on the left-hand side becomes less than 0. So this means that the point AB is a maximum. And there is a third case, okay, which is when delta is less than 0. And in this case, we get what's called a saddle point. So here is an example of a saddle point. So it looks like the path through a mountain range. So in one direction, this point represents a minimum, but in the other direction, it represents a maximum. Okay, so all we've done is analogous to what we already saw for a function of a single variable. Okay, we looked at the derivatives of that function, and we wanted to characterize whether the function was maximum, minimum, or maybe a point of inflection at a specific point. Here we've just got the Taylor series of a function of two variables. Okay, we said at a stationary point these derivative terms were 0. Okay, so the Taylor expansion only involved the function itself and the second order derivative terms. Okay, we just took this to the left hand side to consider the change in the function. Okay, so the change in the function is you start at AB and you move to A plus H, B plus K. And we're asking, is this positive, negative, or something else? Okay, we just did a bit of algebra to rewrite this as something squared plus something squared times delta. And delta we defined as the product of these two derivatives minus this derivative squared. Okay, and if, depending on the sign of f(xx) and delta, you'll either get a minimum on your surface at the point AB, a maximum at this point, or a saddle point. Okay, so just a brief recap of what we saw. We considered a function of two variables, and we thought about the stationary points of that function, and that's when the first derivatives with respect to x and y are both 0. Okay, so this is a stationary point, AB. So at this point AB, df by dx and df by dy are both 0. And we asked, well, what's the nature of this stationary point? Is it a maximum or a minimum of the function? Okay, or is it something else, like the saddle point? And to find out, to characterize this stationary point, we looked at the Taylor expansion, which gave us the difference in the function at the stationary point and some point away. Okay, and we saw that this was equal to this, which has this thing in the round bracket squared. So this term in the round bracket squared is always greater than 0. So the sign of the difference of the function, so how the function changes, does whether it increases or decreases, depends solely on the sign of f(xx) and the sign of delta. Okay, this delta is given by this product of second order derivatives minus this mixed second order derivative squared. Okay, so we said that if delta was greater than 0, then this curly brace term is greater than 0. Okay, so it's only the sign of f(xx) that dictates whether the function increases or decreases. So if f(xx) is greater than 0, then the right hand side is greater than 0. Okay, the right hand side is positive, which means that if you start at point AB, okay, then the value of your function increases as you go to the point a plus h, b plus k. So if you're standing at point a, b, and if you walk in the direction a plus h, b plus k, the function increases, it means you're standing at the minimum. Okay, so that's the minimum. And then the alternative case is if f(x(x) is less than 0, then it means you're standing at the maximum. Okay, so you're standing at AB, and as you move away from AB, the function decreases. Okay, so if you're standing and you walk and you go downhill, then you were at the maximum. Okay, and then we've got this other point where delta can be less than 0, and if delta is less than 0, then the relative magnitudes of h and k will dictate whether this curly brace is greater or less than 0. Okay, and we get the saddle point. But let's think about a simple example. Let's think about the function x squared plus y squared, and let's investigate its stationary points. Okay, so how do we find the stationary points? Stationary points are when f(x) and fy are 0. Okay, so let's find the first derivative of f. So f(x), remember this is just df by dx. Okay, this equals, so we differentiate this with respect to x, keeping y constant, so it's just 2x. Okay, and fy is equal to, that's just df by dy. Okay, we've been lazy, just writing it as fy. This is equal to 2y. Okay, so is there a point at which both fx and fy are 0? Okay, yeah, fx is 0 when x is 0. Okay, and the same with fy. So fy is 0 when y is 0. Okay, so we have a stationary point at the origin, at 0, 0. Okay, so what is the nature of this stationary point? Okay, is it a maximum, minimum, or a saddle point? Okay, so what do we need to do? We need to think about the signs of these two things. So let's think about our f(x(x). Okay, that's the second derivative of f with respect to x. So fx was 2x. So f(x(x) is just 2. Okay, so this is greater than 0. Okay, so we're in the position where it could be this one. Okay, but we need to find out what delta is. Okay, so delta equals fxx fyy minus fxy squared. Okay, we know what fxx is. It's 2. What is fyy? So if fy is 2y, then the second derivative of this, so the derivative of this gives us fyy, and that's just 2 again. So we've got 4 minus, and then fxy. Okay, so this is fx, and if we differentiate 2x with respect to y, then we get 0. Okay, so this is just 4. So delta equals 4, greater than 0. Okay, so here, delta is greater than 0, and fxx is greater than 0. So this implies that the stationary point of this function at 0, 0 is a minimum. Okay, and let's check. Okay, so let's sketch this function. Here's x, here's y, and here's the function z, f of x, y. Okay, and it equals x squared plus y squared. Okay, so we're going to choose values of x and y and see what the corresponding z are. So at the origin, z is 0. Okay, and then as we increase x and y, z increases. Okay. So we have this type of thing, and actually the contours are circles. Okay, x squared plus y squared screams out circle. Okay, and we're saying that this point is a stationary point, 0, 0. And is it a maximum or a minimum? It's a minimum, okay, as expected. Okay, so hopefully that helps. Let's look at a quick example of a saddle point, and that's us done with section 2. Okay, so let's finish off section 2 with just a quick example of a saddle point. Okay, we don't need to think about that complicated function to get a saddle point. We can think about the function that's just given by x times y. Okay, so we want to think about the stationary point of this. So the stationary points are when f of x, which in this case is y, and f of y, which in this case gives us x, when these are 0. Okay, this is 0 when y equals 0, and this is 0 when x equals 0. Okay, so there's a stationary point at the origin. X equals 0, y equals 0. Okay, and the question is, what's the nature of this stationary point? Okay, it's an example of a saddle point, so we should expect a saddle point. Okay, so what do we need? We need to think about the sign of fxx and the sign of the delta. Okay, so what does fxx equal? So fx is y, so the second derivative of f is dy by dx, which is 0. Okay, alright, so we're in neither of these cases. Fxx is not greater than or less than 0, it's 0. And let's just double check, so what's delta equal to? It's fxx. Right, so if fx is y, then we've seen that fxx is 0. So this first term is just 0 minus fxy squared. So if fx is y, then fxy is 1, and 1 squared is just 1. So delta equals minus 1. Okay, so we found that fxx is 0 and delta is less than 0. Okay, so this is a saddle point. Okay, and if we think about what this function looks like, does that make sense? So here is the xy plane. Okay, and our stationary point is at the origin, 0, 0. Okay, when x and y are both positive, then the function is positive. X times y is positive. In this quadrant, it's negative. In this quadrant, it's positive, because it's minus x times minus y. And in this quadrant, it's negative. Okay, so if you start from this point, this stationary point, and you go in this direction, then the function increases. Okay, because this point is 0, so the function at 0, 0 is 0. Okay, so f evaluated at x equals 0, y equals 0 is just 0. Okay, so you increase as you move any direction into this quadrant. If you move this way, you also increase the function. Okay, but if you move into this quadrant or this quadrant, then you decrease the function. Okay, so this is not a maximum or a minimum point. In one direction the function increases, but in the other it decreases. So we've got a saddle point. Okay, and we can think about contour lines. And these are lines of constant z. Okay, so constant z means a constant equals x times y. Okay, so that means that y is some constant, let's call it k over x. So the contour lines look like kind of 1 over x type things, and they're repeated in each quadrant. Okay. Okay, so we can also think about what are called level lines, but let me clean this up a little bit. Okay, so at a level line, or along a level line, the value of the function equals the value of the function at the stationary point. Okay. In this case, as you move away from the stationary point, the value of the function doesn't change, so this becomes 0, which means this right-hand side is equal to 0. So along a level line, you have that hfxx plus kfxy all squared plus k squared delta equals 0. Okay, or that hfxx plus kfxy all squared equals minus k squared delta. Okay, and in this case we're at a saddle point, so delta is less than 0. Okay, so minus delta we can write as k squared mod delta. Okay, this is a positive number. Okay, so this means that hfxx plus kfxy equals the plus or minus k root mod delta. So this tells us that there are two lines with different slopes. Okay, it tells us that we have k times root mod delta plus or minus fxy, so take this to the right hand side, equals hfxx. Okay, so k is the height you move in the y-axis, and h is the x. Okay, so you've basically got k equals hfxx divided by plus or minus root delta minus fxy. Okay, so these are two lines, y equals mx basically. Okay, and the gradients depend on the value of fxx and the delta. Okay, so in this case our fxx was 0. Okay, so one of our gradients was 0, so one of the level lines is the x-axis. Okay, this is a bit of a nasty case because the other line is 0 over 0, which is basically an infinite gradient, and it's the y-axis here. Okay, so along these two lines, the x and the y-axis, the value of the function is the same as the value of the function at the stationary point. Okay, right, that's section 2 done. Okay, hopefully those examples were useful and helpful. Well done on getting this far. Okay, there was a lot of material covered in section 2, but it sets us up very well for the rest of the course. So section 3 should be a lot easier. So section 3 should be a lot shorter, hopefully. Okay. So section 3 will be a lot shorter. Okay, so if you've got any questions at all, okay, if anything is unclear, you don't understand anything, or I've made a stupid mistake somewhere, okay, which is likely, then get in touch, okay, send me an email, send me a message on Teams, okay, or give me a call. Okay, I'm happy to help. I want to help, okay, and that's why I'm here, okay. So don't be a stranger, and just send a message. All right, so well done on getting this far.